Okay, so thank you very much, Russell, for the introduction. My name is Krzysztof Cihoń, and I am mainly senior consultant at Remedo Labs. I am responsible for the consulting, training development in the area of wireless communications and especially 5G. Remedo Labs is a spin-off of the Poznań University of Technology, and it is a consulting and research company focusing on wireless communications, 5G, and beyond, Open RAN, millimeter wave, IoT, Wi-Fi. So these are our main topics. And my speech today is related to 5G millimeter wave. So first, who am I? Who is Krzysztof Cihoń? I work at Poznań University of Technology, where I am an adjunct assistant professor. I am researcher there, and I'm also the teacher. I would like to give greetings to my students, who are also, some of them are present, and also to my co-workers. And then, additionally to this, I am also a trainer and consultant at Remedo, as I put it into introduction this. And finally, I am also I am the R&D advisor at Blair Technologies, which is the company working in the AR and VR field. And specifically, it is also related to cloud-based solutions and precise 5G millimeter wave modeling, and the simulations are done by the simulator from this company. Where is Poznań? So Poland is, well, in the center of Europe. Here you can see there's some photos from Poznań. Quite unusual thing of our city is that it has two castles. It's pretty interesting, and Poznań is 500,000 inhabitants. And also the PUT campus, this is the university campus, where also Remedo has our office. We have about 18,000 students. Moving to the topic. First, I would like to draw some information about millimeter wave, what is it, and how it is related to 5G system. So let's start with the simple frequency line, where you can see some frequency portions. And in standard release 16 of 5G new radio, you can find mainly three new spectrum portions. The first one, 0.7 gigahertz, which is called low spectrum. Then we have 3.4 till 3.6 gigahertz, which is called mid spectrum. And finally, we also have some bandwidth related to the higher spectrum portions. And here, for example, I draw N257's bandwidth portion, which is from 26.5 till 29.5 gigahertz. And this part is called simply millimeter wave. However, what is important, 5G, as you know, is now launched in different portions of spectrum. Also, there are some spectrum taken from other systems, like 2.1 or 2.6 gigahertz. And these three spectrum portions, they are new. That's why I just put it in the slide. And where is the border simply between the millimeter wave and between the other wave? So we used to call, for cellular networks and for mobile systems, we used to call the spectrum sub 6 gigahertz, while the millimeter wave is for sure above 6 gigahertz. This could be a little bit misleading for somebody new in the field, because, for example, for 28 gigahertz, you can see wavelength. It is equal to 10.7 millimeters. It means it is, in the tens of millimeters. However, for the lower spectrum, you have 8.57 centimeters, or even for 700 megahertz, 42.86 centimeter. So usually we use the spectrum below 6 gigahertz. Now 5G is the first new standard which claim at least that the 26 point something gigahertz spectrum will be used for mobile users. And in my talk, I would like also to underline that usually for sub-6 gigahertz, we have urban macro case where the base station is mounted over the roofs, and it's called urban macro case. However, in the second case, urban micro, the base station is mounted slightly below roofs. And this is also pretty important for these two spectrum portions. Moreover, the millimeter wave is of great interest because we have large bandwidth available there. And for example, this bandwidth is also much cheaper. For example, in 2015, and 2 gigahertz, the operator paid $700 per 1 hertz, while in 47 gigahertz, the price was only $2. So that's also pretty great difference. Now I would also like to introduce path loss, since maybe not everybody is deeply in the field, and this is pretty important in my talk. So if we consider base station mounted somewhere and a mobile station, which is user equipment, UE here, then the path loss is simply the difference between the transmitted power and the received power. So it means how much of power is lost in the air in the transmission between the transmit antenna and receive antenna. This is the path loss. And this is important because if you design the network, if you want to check the coverage, or if you want to check the quality of link for the users, if you know the transmitted power, and you have to know the transmitted power, and if you know the path loss, then you can simply determine the received power, which is crucial for users. And mainly in the every case, also in millimeter wave case, in wireless propagation, we have indoor scenario and outdoor scenario. We have also mixed scenario, which is called outdoor to indoor. In my talk, I will focus on outdoor scenario in my simulations. So if we consider the base station mounted somewhere in the city, as you could see in the left side of the screen, then you just launch the power, you just transmit the wave. Then you have simply 4 possible interactions for every wave. And the first is the free space propagation, where we have direct transmission between the base station and the user. Second, we have reflection and transmission case, where the signal touches the wall, touches the obstacle, the building, and some of the power is reflected and some of the power is transmitted into the building. We call it then the penetration loss or reflection loss. Third, we also could have the diffraction case, where the signal goes through the wedge, either vertical or horizontal, and then the signal can bend in the wedge, and also some power is lost in that case. However, this is pretty nice, since users which are shadowed, which are not present in the line of sight case, they could also be served. Finally, fourth, we have also scattering, which is the reflection with the angle which is different than from the incident angle. So this could be understood as the case that the wave is coming to the surface, and then because of the surface roughness, it is scattered with the other direction, with the other scattering angle, and we call it diffuse scattering. So the first case which I mentioned is the free space loss. I would like to compare the millimeter wave free space loss and the sub 6 gigahertz free space loss. The famous Friis formula, where you have received power related to the transmitted power, simply says that this relation, which is path loss, depends on the distance. So the farther we are from the base station, then our received power is decreased with the square of the distance. But also in this formula, we have lambda, which means that the higher the frequency, the lower the lambda. And then for the higher frequencies, the signal is more attenuated. And I compared in the table 3 systems. The first one, 900 megahertz. This is standard cellular network frequency nearly all over the world. The Friis loss per 1 kilometer distance is about 91.5 decibel. Then for 3.6 gigahertz, which is new allocated 5G new radio spectrum, this loss in the same distance is 103.6 decibels. And then finally, for the millimeter wave, 28 gigahertz, it is of 121.4 decibels. So you can see here that the loss between 900 megahertz and 28 gigahertz is around 30 decibel. That's probably a lot. However, there is also good news in this topic. Since the formula, the Friis formula, consists also the antenna aperture, which is lambda over 4 pi squared. And it simply means that the signal is not attenuated in the air. The wave is, let's say, not properly received by the receive antenna, because the antenna aperture simply means, as you can see in the picture, that means the surface from which the antenna can collect the power. And then if we can change the antenna aperture, then we can also, deceive a little bit the Friis attenuation. And the answer on this is, of course, the great topic of MIMO and multi-user MIMO. Here you can see on the right the 3 sets of antenna arrays. It's 2.2, 4.1, and 4.4. And you can see the more elements in the antenna array we use for beam forming, then the beam is more narrow, which means it has greater directivity, which means the user in a given distance will collect greater amount of power. Second, we have the reflection loss and transmission loss. Here you can see the base station and, of course, the wall, the building. And the rule of thumb says that if the wave transmits through the obstacle of the size similar to wavelength, then it is significantly attenuated. So if the wavelength is greater than the obstacle, then it quite easily can propagate inside the buildings. However, if the wavelength is much lower than the obstacle width, then it is significantly blocked. Of course, it doesn't mean that if you compare, for example, 6 gigahertz wave and the lambda is around 5 centimeters there, it means that if you transmit over the wall equal of the width with the width of 5.1 centimeter, then it is blocked. But if the wall is 4.9 centimeter, it goes easily. Of course, it is smoother. However, the rule exists. And if we compare the reflection losses regarding the frequency and also the transmission losses, we could observe the frequency dependence here. On the right side, you could see the @C document, where some penetration losses are given in a quite simple way, where they are based also on the frequency. And you can see that If we talk about wood or glass, then there is no great dependence on the frequency with the penetration loss. However, if we talk about concrete, then the penetration loss is much more dependent on the frequency. And in the millimeter wave, we can assume that the wave is even completely blocked. Moreover, this is one of the, I guess, famous picture related to the millimeter wave attenuation. The source is on the right side. The measurement equipment here was located in the degree of 45 degrees from the wall. And the guys who made these measurements, they simply moved the transmit antenna and receive antenna along this wall. And they wanted to check how different walls or windows attenuate the millimeter wave signal. And as you can see, for dressed stone wall, first, the attenuation was quite significant, and second, it was quite unstable. However, if we consider window or bath stone, then the attenuation was lower and moreover quite stable when they were moving along this wall. So the conclusion in the reflection losses is here the following. We could observe greater losses. Even the difference could be of 20 decibels regarding the materials. And the other thing also here is important that it is quite hard to measure. I mean, the penetration losses and reflection losses, the exact values, but we can assume that the penetration losses, for example, they are of 10 decibels different, for example, between 30 gigahertz and 2.6 gigahertz. Diffraction loss, that's the next topic important in millimeter wave. Here you can see our faculty premises. This is the measurement conducted with Karolina Uszyczyn. This is the diffraction wedge on the right side. Maybe you could see my... on the right side, you could see the antenna. This is the transmitter. The wavelength is, the frequency here is exactly 28 gigahertz. So it is directed exactly to the wedge of the building. And this is the other view of this. And then here there is the other wedge, I mean the other side of the same wedge. And this is the receiver antenna. And the measurement was the related to the what is the loss of the diffraction when we compare 2.45 gigahertz and 28 gigahertz. And the results are quite interesting. Here you can see that the dashed line, they are theoretical line, while the solid lines, they are measured values. And the average difference between the measured values or theoretical values, they are about 10 decibels here, at least 10 decibels. Of course, the greater the diffraction angle, the more we are hidden by the wedge, the attenuation is greater of the diffraction. However, still, this diffraction loss, it's not killing the propagation in the millimeter wave. It is bigger than in sub 6 gigahertz, but it is not killing the case. And just to sum up the diffraction, so we have 10 decibels difference. We could model this with a couple of methods. The Daegu method is the theoretical method for the diffraction modeling. We also have quite a popular Berg iterative model and quite a detailed UTD, GTD precise model. And scattering, which is well, of great importance in the millimeter wave, we shall consider the Rayleigh criterion for surface roughness, since if we have millimeter wavelength, we have a couple of millimeters, then we compare the wavelength of the wave with the roughness of surface. And if they are of the similar size, then the scattering plays a main role here. All right. Now let's move to the millimeter wave channel modeling. So let's move to the small city in northern Poland. Here you can see the Google Maps satellite view, and you can see some buildings. If we have some drones which are flying here, and then based on these missions, we can have point cloud. So this is the map, 3D map, where the buildings and trees and foliage, and every car is here present as a point. You can see now a little bit zooming in, and then you can see single points. Then this point cloud is changed into the digital map of this scene, and then you can see 25 centimeters accurate model, which is the input for the ray tracer, for the detailed engine. And then if we mount here the antenna and the building, then we probably shall see the street along which we can propagate the wave. And the good news is that we don't have to think more a little bit about it, because we can see simply how it looks like. This is the real photo, and even the antenna is put here, that you can really imagine now the signal is going here along the street. The sea is just well, just behind this hill, the Baltic Sea. All right. And now I would like to move into the modeling. This is pretty important for the planning staff, for the engineers who plans the networks. Probably the older remember perfectly the famous HATA model. It was found in mid-80s, and that was the model given by the following formula. Of course, this model is applicable to the frequencies below 6 gigahertz. Probably the basic HATA model is up to 2 gigahertz. The extension is up to 2.5 gigahertz. However, here I would like to compare this old model, and I just here you have the formula, and the path loss depends on the frequency given in megahertz. You have some coefficients related to the base station height. Also, mobile station height is included here. And finally, D is also given in kilometers. That was the time that we planned the networks for kilometers. Now we have tens, hundreds of meters. And then if we move, if we put into the formula 30 meters for base station height and 1.5 meter for the mobile station height, the formula is a little bit simplified. Here we have three components: the one related to the distance, the second is the constant value, and the third related to the frequency, given right now in gigahertz. And if we have the plot of this in the city, the base station is mounted here, it's dot point A, then simply the path loss depends on the distance. So if you are the user and if you are in the point B or C, which are of the same distance, then your path loss is exactly the same according to the HATA model. And this is the simulation result for our small city in northern Poland. You could remember, according to the HATA model. And so that's irrespective of where we are, if we are in the shadow of the building or if we are in the line of sight, the path loss is similar. And of course, the measurements say the opposite. That can't be true. If you are in the line of sight, the red line, probably your situation, wireless situation, is much better than if you are in the non-line of sight. Here, the measurements were conducted in 3 streets: the blue, green, and black one. And these, here we are the results. The source is the Metis final report, really nice document. And here you have the measurements and theoretical lines for 6 frequencies. I think the most interesting for us is 26 gigahertz case E, where you have a line of sight path loss given in red. Red circle, these are the measurement points, or however the line red solid is the theoretical line. So in the line of sight case here, the path loss is above 100 decibel. For example, 200 meters, it is around 105 or 110 decibel. However, in the non-line of sight cases, it is much lower. It depends on the street. It could be even 140 or 50 decibel, and depends on the street here. And this relation, I mean the difference between line of sight case and non-line of sight case exists in every case, irrespective of the frequency. So, why not to distinguish in the propagation model these 2 cases, line of sight and non-line of sight? And this is the class of loss and loss-aware empirical models, where you have to know if you are, if the user is in the line of sight case or non-line of sight case, and then you have 2 formulas. And distance dependence is different in these 2 cases. Line of sight, of course, is more optimistic. And our simplified scenario with base station mounted in point A and locations of user in points B and C. And now their situation is much different. If C user is in non-line of sight case, so it's simply shadowed by the building, then the path loss here is much greater. However, the user B is in the line of sight case, so his attenuation is lower, path loss is smaller. And this is the comparison to previous obsolete HATA model. All right, and this is the result for the loss and loss-aware empirical models. So right now, there is a great difference between line of sight case and non-line of sight case. So if you go along the street and the base station is mounted in the end here, your wireless situation is much better, which means simply that the path loss is lower than if you are in the non-line of sight case. Here, this part of the results is related to the building, because the antenna is hidden a little bit in the building. That's why here we have non-line of sight case. And the comparison between these 2 simulation results are the following. The millimeter magic, of course, is much more practical. The third class of modeling, so the first was empirical obsolete HATA model, the second line of sight, non-line of sight aware model. The third class is ray traced or ray launched modeling, which involves, of course, the digital scene of the city, digital map of the area. And here the comparison of ray tracing and ray launching is given. On the left side, you have the room, and ray tracing simply means that you simulate every single ray inside the room, and you have the transmit and receive antennas, and you, based on the assumptions, reflections number, for example, or diffractions number, you simulate each single ray. However, in the ray launching, you just launch the rays from the transmit antenna, and the alpha parameter, the density of rays, is crucial, since the greater the density in the engine is, then the greater accuracy of results is given, of course, under the cost of complexity, under the cost of calculation complexity. And the environment resolution also is here pretty important. And this is the result from WinProp Ultra Echo software. You have the base station here. This is similar, the height of the base station is similar with the rooftops, and you can see a couple of rays coming from the base station to the user located here, and you have the diffracted rays and reflected rays. So in my ray tracing results, the scene is of size 460 meters per 280 meters. Then we have urban micro case, which means the base station is mounted slightly below the buildings. The maximum building height is 17 meters. The average is 15 meters. The base station height is 8 meters, and the transmitted power is 20 dBm. The results are given in the received power. So this is the ray tracing results for zero reflections and zero diffraction. So you can see nothing is reflected simply. You have some foliage given in the violet color. These are the buildings. The scene is simply cut in the given height. So you can see here that you have some foliage attenuation only and nothing reflects. If we increase by 1 the reflection and the diffraction, then we have the following scene. So it looks like it is much better if the user is in the non-line of sight, then he or she can simply collect much power, especially if he or she is close to the antenna. Then if we move to the 2 reflections and 2 diffractions, then the number of rays is much denser, and 3 reflections and 3 diffractions give us even a greater boost in the number of rays. We can see that the coverage is right now quite nice. So all cases together, let's compare them. So if we have here all cases together, of course, the more interactions we use, the more reflections or diffractions we use, the greater accuracy of the scene. All right. So this is ray tracing, ray launching results for detailed network planning. And now a few words about millimeter wave adjustments. First, rain or snow. now we have snow, at least in my country right now, which is starting to become more and more unusual. So if we have rain of, for example, 100 millimeters per hour, this is really heavy rain. And if we consider the frequency of, for example, 30 gigahertz, then the attenuation is around 20 decibel per kilometer, which means it is 2 decibel per 100 meter or 4 per 200 meters. So that becomes it becomes to be significant value when we want to find a link budget. Then we shall include also the possibility of rain attenuation. Of course, the rain or snow is quite important for direct links in millimeter wave, since these frequencies are in current use in the backhaul links, not only in 5G but also in the previous systems. The backhaul direct links, when we have two antennas with great directivity, and the operators they find the link between one base station and the other and send all of the traffic from one base station to the other, for example, central base station. So that's quite important there. Here it is not of so great importance, however, it becomes visible. And if we compare these 2 decibel per 100 meter to 3.6 gigahertz, then we have the attenuation there is only 0.03 decibel per kilometer. So it is completely invisible for operator and users. Also, gas attenuation becomes visible in millimeter wave. Fortunately for the 30 gigahertz, it is really low. It becomes well visible in a greater set of frequencies. By the way, the predictions are that in the future systems, including 6G, which is which is now in the research, the predictions are we will use higher frequencies than 28 or 30 gigahertz. So probably this is the time to touch this topic. If you look into 28 gigahertz, the attenuation is 0.05 decibel per kilometer. However, for 60 gigahertz, it is 20 decibel. It's here 20 decibel per kilometer, so it's still quite a lot. And foliage attenuation. Probably you remember today I mentioned that a rule of thumb says that the wavelength should be compared with the obstacle width, and if the wavelength is of the similar size of the obstacle, then we have greater attenuation. So it also is related to the foliage. If our wavelength is 1 millimeter or 10 millimeters, which is 1 centimeter, then the foliage, which is quite often of that size, it starts blocking millimeter wave. And in the ITU recommendation P.833, you can find that in woodland for 2 gigahertz, the attenuation is 0.4 decibel per meter. However, for 30 gigahertz, it is attenuation is equal to 6 decibel per meter. So it's not mild scatterer as it was for the sub 6 gigahertz cases. Now in millimeter wave, it is pretty important to include foliage into the simulation. And right now I have the film which compares two things. The first is the foliage attenuation. Here you can see top side view on the scene, and the purple is the foliage. And here on the right side is the side view of the same scene. The purple again is the foliage. This is the real, of course, scene, the real foliage taken from the digital map. And also the precipitation, the rain is given here. The description is here at the bottom. So let me check if it works. So now we have 3.5 gigahertz. Now 3.5 with rain, the difference is not very significant. Now we move into 26. You can see greater attenuation because of foliage. And with rain, it is also a little bit slower. I mean, attenuation is greater. And finally, 64 gigahertz, the coverage is really limited. If the rain comes into play, it is even more limited. So that's the film. And the final topic is AI-based channel modeling. Here I would like to put only a few thoughts in the field, since the artificial intelligence and machine learning, it is coming to wireless field also, to the network planning also. So a few things. First, about the application in the wireless field. So in principle, machine learning or the artificial intelligence, it is inferring based on data. If you have data, the more precise and clean data, the better. Then based on the data, you just infer how the system works. But in the reality, I mean, in the wireless field, we have quite often nice models. We could model how the wave interacts. We could model exactly the working of the whole engine, the working of the field. And the AI here may significantly reduce the complexity, computational complexity. And this is probably the main point here. Then, in the ideal case, we shall have the measurement data, plenty of the measurement, real well-prepared data, and then we put this measurement data into the engine, and based on this, we could produce the path loss results. And this is in current research and application stage. People all over the world, they publish papers, they implement artificial intelligent solutions, AI-based solutions. And I have here two examples of application of this AI in the field. First, the diffraction loss prediction. The case here is that I mentioned the diffraction. So that's the case in Korea, where there are some hills, some mountains, and this is the model, theoretical model for the diffraction. And these are the measurement results in this hilly terrain in the Korea. And the guys, Lee and Park, they simply put the measurement data into the engine and then just inferred with the proposed method what is the diffraction loss. And here there are 6 colors in the plot. So the main one is the blue, which is the measurement data. You can see that it is of a great change. And the proposed neural networks based solution is the red one, the red curve. And their error was around 3 or 4 decibels when compared to the other methods. Theoretical one, the error was 7-6 decibels. And this is one of the examples how the deep learning simply can work in the field. The second one is given by my student, Supavat Tamsri, which is quite talented guy. He built an 3D scene of the, by the way, this is old market square in Poznań. and he built the stage. And he learned a model. He just used ray tracing here with the diffraction, reflections also. And based on the results of the diffraction and the reflection, he just found the path loss in different cases. And then he put the gradient ascent method with Adam optimizer. And then he planned the small base stations in this area. Now I hope it works. Okay. So based on the random set of users, blue dots, and based on their link qualities, which is related to the propagation, he found the locations of base stations, small cells. They are red one. And this is the example how the algorithm looks for the best solution, best location of base station. This is based mainly on the line of sight case. Non-line of sight case is here under further stage, and then you can find in this link his work and read more details. So just to sum up, honestly speaking, this algorithm here, it is not AI, in principle, since there was no data, measurement data or other data based for learning and finding the positions of the base station. That was the enhanced optimization problem where they were many iterations with gradient ascent method, which is one of the probably well-known methods in the machine learning field. And that's the case that with these optimization methods, machine learning tools and AI tools, we can faster get best or close to best solutions. And this is a new tool in our field. And I think that now it's the time to learn this new tool, which is simply used for solving problems. So if you have great data, for example, ITU recent challenge put LiDAR data. LiDAR is a kind of the radar where you have the scene, a 3D digital scene, what the base station can see. So they compared these LiDAR data, and the case was to find the beam pattern, because in the mmWave and the MIMO, the beam selection or beam finding is one of the crucial problems right now. So if you have nice data, then you can go simply with AI. Also, the AI is maybe used if you want to find not well-modeled cases like user mobility prediction. It changes every time, especially right now in the COVID time, it changes significantly because of more remote work. And then also the traffic prediction based on time and space correlated data could be done here. But if we go into the wireless modeling field, my personal point of view is that it may often fasten the finding solutions to the given problems. And now this is the time to work on this and to find these new solutions. And conclusions. All right, so first, detailed modeling is pretty important in the mmWave, especially if we have a dense urban scenario. Then it is even more important if foliage attenuation or dense, I just mentioned it, if the foliage attenuation is included. Of course, if we want to have higher precision, then greater computation resources are needed. However, innovation comes unexpectedly quite often, and maybe AI, which is around the corner, may change the game we are playing at, and maybe with AI we can simplify the implementation of a precise modeling, and we can simply make it faster, simpler, and better. That's my final conclusion. Thank you very much for the attendance. Thank you very much to Russell for the introduction and to I could serve here as in this webinar. Thank you also to Abhijit. Thank you also to the other people, Marcin mainly, also Łukasz, and others who helped me a lot in this webinar to find this stuff here. Also, this is, for me, it is really exciting that I saw here people from all over the world. So I saw Panama, I saw Kenya, I saw also Estonia, US, many countries. So thank you for the attention. I also want to switch into the second computer, and maybe 2 more minutes would devote to the simulation.
Why don't you go ahead and get started with that, Krzysztof? And thanks so much for that presentation. It was really tremendous. We had several questions while you were presenting. I flagged some of them, and if you've got some time, we'll try to get to those. For those of you who attended, thanks so much for being here with us. I know you're all busy and taking time out of your Saturday. That's expensive for you, so thank you very much for joining us. Krzysztof did say some thanks out there. My partner, Abhijit Kumar, also to Marcin Dajinski. I'm sorry I butchered your family name. He's also with Remedo Labs. Also, the gentleman from Blair.tech made a couple of comments about his, I think his modeling software was used a little bit. Is that correct, Krzysztof?
Yes.
Okay. Well, that was very nice.
I would like to show it because I have real time working modeling right now, so I could just open the tool and then show it. Now you shall see the scene. Can you see the scene?
Yes.
All right, so this is the same scene as I showed in the presentation. So right now you can see the foliage and buildings, and let me launch the reflection 1, and maybe reflection start with 0 case, reflection 0, diffraction 0 case. Let me start the propagation. So this is the result. We could cut the scene in the various directions. So this is the result of the single reflection, single diffraction. We could go up, also, and down, and then reflection 1, diffraction 1. So these are the results. So this is launched in my notebook, and it is given in the real time. You can see here the number of rays founded. Right now we have 1.5 million rays. And then we have reflection 2 and diffraction 2. Maybe once again. Right now, yes, it is here. So these are 2 reflections, 2 diffractions. Then let's move to 3 reflections, 3 diffractions. So clear, and now launch the simulation. And now you can see the results. If you want to cut it.
Chris, when you change the parameters, it seems to generate the model on screen very quickly. Is this a special computer? Is it a very strong processor, a lot of memory, or is it just very efficient at computing the result?
Well, this is a notebook with the graphic card, And
Okay.
this processor here is probably i7, so
Yeah.
it is rather strong. However, it is not top. Well, this is quite mid-strong, and it is it is calculated in real time. Here you can see, for example, for 3D fractions and 3 reflections, you had 3 seconds, 3.5 seconds, and you have 6 million rays found.
I'm very impressed by that. That's really terrific.
So here is the scene, and of course also we can find the the simpler models like mmMagic. They are pretty fast. So these are the results which I showed you in the presentation. So I am also impressed. By the way. All right. So that's what I wanted to show right now. Okay. So thank you very much.
Wow, tremendous. Do you have a little time to consider some of the questions from the attendees?
Yes, we can go with some questions, of course.
Okay, so I'm going to go back here, and some of them are flagged. Well, so many comments here, yeah. Let's see. The students themselves are also able to flag the questions, so and not all of them have been filtered. So and I've lost the ones that I had. There was a question though. Can you say a little bit more about the modeling software, the Blair.tech software? There was a question about free software for doing ray tracing. Is the Blair.tech, is it in the public domain, or is it a commercial product from Blair.tech?
Well, this is the question. So it is not released in commercial so far. However, as you could see, the stage of the software right now is quite mature. So I guess it will be released in the future time. So it is not available in the public domain. However, I guess that in a couple of weeks there will be a kind of release or the webinar or the some information related to the to this. So well, I think you can simply go to the web page, and just to observe LinkedIn profile. Also, well, I would like to encourage everybody to connect with me in LinkedIn. I will really appreciate it, and maybe to get some feedback information from attendees. That's really, really nice.
Okay. In the beginning part of your presentation, after you had talked about the foliage and the rain fade, there was a question about, you mentioned loss due to gas. Were you just talking about the difference? You gave a sea level example. Was it just the difference between basically air density at sea level versus at higher elevations?
What is the difference in the attenuation between sea level and the higher levels?
I think the question was, what was the gas, and were you simply trying to illustrate how the air at sea level? Go ahead, please.
Okay, so this attenuation is is related to the particles of gases. For example, the first attenuation peak. I don't have presentation in this computer, but sorry, as I remember, 60 gigahertz, that was the first peak. That is related to the oxygen attenuation. So this is related to the particles which are in the air. That's the reason. But this is the really good question, how it is related to the density of the air, since in the mountain we have lower density of air. So we can assume that there is a lower number of particles, so maybe the attenuation is lower. Okay.
It's interesting that at 60 gigahertz, we now have to start taking into consideration the chemical composition of the atmosphere. I don't ever remember hearing that at 700, even into 2.3, 2.5 gigahertz. It just was never anything I remember hearing about. Okay, so I am going to put your LinkedIn, the URL to your LinkedIn account. I'm going to put that into chat. But
Yes, perfect. And just to ask, just to send me invitation, I will probably accept everybody.
Okay, now everybody go on to LinkedIn and try to send a connection
So I can, well,
to Krzysztof, and we'll
I
see
don't
if we
know
can blow up his LinkedIn account.
how I can just post it, of course, as you would like.
I'm sure I'm misspelling your name. I'm so sorry. Okay, I've just put his LinkedIn, the URL to his LinkedIn
Thank
account.
you. I would also probably next week I will release the other posts because in the Remedo we also have a blog post. We just release the knowledge. This is our mission. So we will also just post next stuff. So next week, fortunately, we'll have next post. So we also could just invite people to observing our page, Remedo Labs, and to subscribe newsletter.
Okay. Is there? I'm going to ask. People. There were so many people interested to hear your presentation today. If there's some other aspect of modeling that you'd like to present, we'd love to have you back at a later time. I know you're busy, and this is a orthogonal, what you normally do. But
yes, the topic is really broad, and today I selected just main stuff. I mean, the difference between sub 6 gigahertz and millimeter wave. That was the first main topic. The second was the how to model this, and a little bit about AI. There exists other stuff like, for example, satellite communications. I got the questions on this. That was not addressed today, but well, yes, I really love teaching, so that's really exciting for me just to have webinar and just to release knowledge. So yeah, if it is possible, Russell, from your side, I guess, well,
we'll talk about it. I'd love to hear more, and I think the audience would as well. Just judging by the interest in this presentation. At the outset, you gave a little bit of a very brief bio of yourself. Could you say, since most of the Cafe Tele audience is focused on mobile telecoms, could you say a little bit more about the work you and your lab are doing with some of the operators there in Poland?
You mean the Remedo Labs?
Well, or in your university work. I'm just curious, since many of the audiences really applied RF.
Okay.
They're not academic; they're out in the field using, so they might be interested to hear a little bit about what your exposure is to the actual mobile.
Okay. I did my PhD at university in 2017, so it's roughly 4 years since I did my PhD, and I'm in the Institute of Wireless Communications. So my PhD was related in this field. I also worked in the operator, but that was a couple of years ago. I worked as a network planning engineer, and I think this is also one of my interests right now. So that was also probably the point of view in the presentation was also how to plan this. And I think the topics like automatic network planning or the detailed, propagation modeling, they are in the current interest. So that's my interest. But the question was about my field. Yeah, so that was the operator. And at the university, we have also, a couple of projects which were also related. The great part of these projects are scientific projects. They are funded by the national government entity called National Science Center. We also, thanks to Professor Bogucka mainly and Professor Kliks, we also were related to some European projects, also included in Horizon 2020. So there is a deep field in this. I also work in the IRACON, which is the Network of Excellence. So I collaborate with the research guys from Europe. Right now also there's the special group related to the electromagnetic exposure which is the hot topic. People are afraid of exposure and afraid of 5G. So, well, we are discussing it from the scientific point of view. So this is my background. 3Meadow, which is the spin-off. It is quite newbie. This is a new company. This is a spin-off. We have some consulting and also some projects in the implementation field. Yeah, so that's my background.
Super. Well, I want to thank you once again for sharing this with us today. It's been a very interesting session, and we'd love to have you back again sometime if that would fit into your schedule, and look forward to talking to you again. I want to thank everybody for joining us once again. It's a great session, and appreciate you being here with us today. I've posted the link to Krzysztof's LinkedIn profile. Feel free to connect with him so you can see what routine updates he posts there on LinkedIn. I've also posted several times the URL to where we host our recordings of this webinar and our past webinars and trainings. I'll be sending out an email to all of you that registered today, and in that email I'll include a link to the replay site. The replay site will also have, Krzysztof, is it fair? Can I get your presentation as a PDF so that people who want to review your presentation in a PDF format, is that okay for you?
For me, yes, sure.
Yeah, okay, good.
I will. Yeah.
People always want to have even if they watch the video again, they typically like to look at the presentation again as well. So I'll ask for a copy of that and post it as a PDF right beside where the recording is. With that, I will say goodbye and final thanks to Krzysztof, and we'll see you next time. Have a great weekend. Thanks so much.
Yeah, thank you. Bye.